300 million light-years away deep inside the galaxy, NGC 4089 lies one of the largest black holes ever found, but it's completely silent. This sleeping giant holds mysteries that challenge everything we know about the universe. If you enjoy calm cosmic journeys, please subscribe and share, and tell us in the comments, what do you think could wake a black hole from its sleep? Thank you for watching. Now, let's begin. The Coma Cluster stands as one of the largest concentrations of galaxies in the nearby universe, and it sits at a distance of roughly 300 million light-years a distance that places it beyond the Virgo supercluster neighborhood as seen in astronomical surveys. Astronomers call a gravitationally bound group of many galaxies a cluster, and this cluster is a clear example of the large-scale structure of matter. In 3 dimensions, these galaxies occupy a region that spans many millions of light-years across. The shapes of these galaxies are scattered within this volume, yet they remain gravitationally tied together by the shared mass inside the cluster as a whole. The view that telescopes construct uses imaging of light at different wavelengths to isolate how galaxies appear individually and how they group into larger systems. This cluster is a dense environment that still contains voids, smaller subgroups, and slower transitions in galaxy density at the outer margins. The Coma Cluster is not a uniform field. Instead, it is shaped like a rough 3-dimensional cloud containing distinct concentrations of elliptical galaxies near the cluster core and spiral galaxies more evenly sprinkled in the peripheral region. It is this outer region that remains the first frame of context for this documentary, because it sets the broad stage before any deeper inward move toward a single galaxy. The cluster is so massive that its presence curves space-time enough to generate weak gravitational lensing in the light of distant background galaxies. That distortion allows astronomers to estimate a mass that is far larger than the visible matter alone can account for. This in turn signals large reservoirs of dark matter within the cluster volume. Dark matter is a form of gravitational mass that does not shine and does not interact with light, and it is invoked because the gravity we measure exceeds the gravity expected from the stars and gas alone. Thus, the Coma Cluster becomes not just a gathering of galaxies, but a gravity well carved out by a huge combination of stars, gas dust, and unseen mass that can only be inferred. The cluster environment is also filled with extremely hot gas that is ionized, meaning electrons have been stripped from atoms at temperatures of tens of millions of degrees. This gas is not star forming because star formation requires cold molecular gas that can collapse under gravity. Instead, this hot gas emits X-rays. Observatories that detect X-rays reveal maps of the intracluster medium that surrounds and permeates the gravitational basin. When an astronomer points an optical telescope and an X-ray telescope to this region, the optical data show the galaxies themselves, while the X-ray images map the hot gas that surrounds them. The scale and the temperature of this X-ray emitting gas confirm that the cluster is stable and gravitationally bound on a very large scale. The galaxies move through this intracluster medium and they experience ram pressure as they fall toward denser zones. Outer layers of gas that once may have been in a galaxy can be stripped by this interaction. Spiral galaxies often lose some of their cold gas when they travel through dense intracluster gas. Over time, that loss slowly changes the behavior of star formation in cluster galaxies. Seen from very far away, the Coma Cluster reads as a crowded region of luminous points when imaged in visible light. Each point is an entire galaxy, not a single star. When the telescope gathers more light, these points resolve into shapes and structures, some round, some elongated, some smooth. The overall composition is dominated by elliptical galaxies that have older stars and a more diffuse shape. The cluster is a giant environmental container that shapes galaxy evolution on long timescales. Within this huge region, galaxies interact not through direct collisions alone, but through long-range gravitational tides and through the movement of gas they encounter at high speeds. The high density of galaxies increases the probability of gravitational nudges that redirect the orbits of galaxies inside the cluster volume. Large clusters like this produce few new stars because the cold gas required for star formation is scarce. The hot intracluster medium does not cool fast enough to condense into stars. Instead, galaxies consume their internal gas over billions of years, and after the supply of cold gas runs down, star formation slows. This cluster is a site where elliptical galaxies have become common, in part because many galaxies that enter the cluster eventually lose gas and become smoother and more spheroidal shapes, especially if they are pulled and stretched by tides, or if their cold gas is stripped by the intracluster medium. The Coma Cluster is also a place where gravity holds the entire structure together in a stable configuration. Observations that measure the velocities of galaxies within this region confirm that they move in ways consistent with a system held together by a mass larger than the individual galaxies combined. Each galaxy is a small unit, yet the cluster as a whole generates the force that binds them. That gravitational binding ensures that the cluster does not simply dissolve, even over very long spans of cosmological time. The cluster has substructure. Some subclusters merge into the main structure, and they bring their own galaxies and dark matter halos into the larger composite mass. This cluster environment is where the very first scale frame of this narrative sits. The cluster sets the outer boundary for everything that follows. Within this boundary, a great collection of galaxies can be found, and one of them holds the ultramassive black hole that this project will eventually reach. But none of that information can be examined until the environment defining the total gravitational context has been laid out. All light that reaches telescopes from the Coma Cluster has travelled for hundreds of millions of years, so the image we see records a past era. The distance to this cluster means that the light left its galaxies when Earth was a different planet in a different period of geological evolution. Yet in cosmic terms, this region is still regarded as relatively nearby, because the observable universe contains structures that are billions of light years away, and the Coma Cluster sits in a zone that has been mapped with high precision for decades. Thus, the Coma Cluster forms the outer regional stage on which the galaxy known as NGC 4889 is located. The intracluster medium in the Coma Cluster is a very hot and very diffuse ocean of plasma, and it fills the spaces between galaxies rather than within them. Plasma is a state of matter in which gas becomes so hot that electrons no longer remain bound to atomic nuclei. This medium contains ionized hydrogen, ionized helium, and trace heavier elements that were created inside stars long ago, then expelled into space by stellar winds and supernovae. The temperatures of this intracluster gas reach tens of millions of degrees Celsius, and at these temperatures the atoms are fully stripped of electrons. Such gas does not radiate strongly in visible light. Instead, it produces most of its radiation in the X-ray band. An X-ray telescope pointed at the Coma Cluster reveals a luminous haze of X-ray photons from this hot medium. Optical telescopes show the galaxies themselves, but they do not show the intracluster gas directly, because the gas is too hot to emit most of its radiation in visible wavelengths. The presence of this hot gas tells astronomers that the cluster has been deep in gravitational equilibrium for a very long time. The gravitational potential well of the cluster compresses this gas. When a gas is compressed and held in a deep gravitational basin, it heats. The hotter it becomes, the more strongly it radiates in X-rays. Since we observe strong X-ray emission from the Coma Cluster, we know that the gas is very hot and very widespread. It fills the volume between galaxies, and it also offers an environment that can strip gas from galaxies. When a galaxy falls into a cluster, it does not simply drift. It travels through this hot plasma and experiences ram pressure. Ram pressure is similar to the force one feels when moving quickly through a dense fluid. At very high speeds inside the intracluster medium, gas can be removed from a galaxy's halo or from its spiral disk. This process limits further star formation, because cold molecular gas is required for new stars to form. When a galaxy loses its cold gas, it stops making new stars, and the existing stellar population grows older and redder. That is why so many cluster galaxies are elliptical or lenticular and have little ongoing star formation. The intracluster medium shapes galaxies over billions of years. The stars in a galaxy remain gravitationally bound to the galaxy's own mass, but the diffuse gas in the outskirts of a galaxy can be lost to the hot cluster medium. This loss changes the composition of galaxies slowly and steadily. The plasma that fills the cluster is not uniform in density. It is denser near the center of the cluster. Toward the outskirts, the density decreases. Thus, the environment changes smoothly from the outer boundary of the cluster toward the core. The deeper inside the cluster volume a galaxy falls, the more strongly it experiences ram pressure stripping. X-ray maps of the Coma Cluster show that the cluster has a bright core region where the gas is very hot and very dense. This core region is where the largest elliptical galaxies tend to be most common. It is also where the intracluster medium is thick enough to strongly influence any galaxy that enters this region. The hot gas is enriched with heavier elements produced in ancient stars. These elements were distributed into the intracluster medium by supernova explosions in early epochs of galaxy formation. The intracluster medium thus contains chemical evidence of stellar evolution that occurred long ago. When astronomers examine X-ray spectra from this region, they can determine how many heavy elements are present. That inventory helps reconstruct the history of star formation and supernova activity in the galaxies that contributed gas to this medium. The intracluster medium is not static. It moves, circulates, and responds to very slow flows driven by the cluster gravitational field. Subclusters or groups of galaxies that fall in from the outskirts can bring their own gas with them, and when they merge with the main cluster, turbulent flows can mix the intracluster medium. Some of this turbulence is large-scale and can persist for hundreds of millions of years. On these timescales, the intracluster medium can redistribute energy and momentum across the cluster volume. That energy budget is measured in the form of temperature maps and luminosity maps constructed from X-ray data. Very hot gas emits X-rays strongly. If a region is cooler than its surroundings, the X-ray emission will drop in brightness. Observing these brightness patterns allows astronomers to identify regions of increased density, subcluster infall, and past interactions. The presence of this hot gas means the cluster is not a gentle field of isolated islands. Instead, it is an environment where galaxies move through a thick ocean of ionized gas. Stars within each galaxy do not collide directly with this gas, because stars are very compact compared to the average free path between charged particles in the intracluster plasma. But the gas in the galaxy halo can experience friction against the intracluster medium. That friction can strip gas away and deposit it into the cluster medium. The Coma Cluster intracluster medium is therefore both a record of past galaxy activity and a driver of present galaxy evolution. It is a reservoir of ionized gas warmed by gravitational compression and heated further by occasional shock waves caused by the motion of subclusters or galaxy groups falling inward. These shock waves show that the intracluster medium can change locally over time. The intracluster medium is also a tracer of the cluster mass. To hold this hot gas, the cluster must have deep gravitational potential wells. The mass required to keep this gas gravitationally bound is much larger than the mass of stars alone in the cluster galaxies. That mass is attributed to dark matter. Thus, the presence of the intracluster medium indirectly confirms the large dark matter content of the cluster. The hot gas follows the gravitational contour of the underlying mass distribution. Where the dark matter density is higher, the gravitational potential is deeper, and the gas becomes denser and hotter. The intracluster medium therefore serves as a visible X-ray indicator of the invisible dark matter halo of the cluster. All of this confirms that the cluster is a gravitationally dominated system in which galaxies are embedded in a dense plasma that influences their long-term morphology, color star formation history and gas content. This intracluster medium forms the environmental stage that sits immediately inside the cluster scale, but outside any specific galaxy. When placed in context, the intracluster medium functions as the sea through which each galaxy moves, and because this plasma is hot, sparse, and massive in total volume, it is a defining feature of cluster astrophysics. It is within this medium that NGC 4889 resides, and this continuous hot plasma bath sets the conditions for any galaxy that exists in the core region. The Coma Cluster displays a diverse population of galaxies, and they are not arranged in a simple pattern, but instead exist as a complex mixture of types spread across the cluster volume. Spiral galaxies with their distinct disks and arms tend to be found more often in the outskirts of the cluster, while large elliptical galaxies populate the denser regions near the core. This distribution is not random. Rather, it reflects the long-term dynamical behavior of galaxies that have fallen into the cluster gravitational well. Galaxies that approach from the outskirts may remain spiral systems for long periods because they retain enough cold gas to continue forming stars. But as they sink deeper into the dense intracluster medium, they slowly lose their cold gas. This loss reduces star formation, and over very long times the galaxy may become dominated by older stars and adopt the smoother appearance characteristic of elliptical galaxies. Spiral galaxies can maintain their structure until they reach environments where the intracluster medium is dense enough to strip cold gas from their outer layers. Elliptical galaxies, which generally lack large amounts of cold molecular gas, are older systems that contain evolved stellar populations. This population mix becomes a tracer of how long a galaxy has been subject to cluster conditions. Thus, the Coma Cluster is a dynamic system in which galaxies migrate both spatially and in their internal structure over cosmic time. The overall galaxy distribution within this region is mapped by deep imaging surveys that measure the shapes, brightness profiles, and spectral signatures of each galaxy. Optical surveys show that the number of elliptical galaxies rises sharply toward the cluster core, while spiral galaxies are more evenly represented at intermediate distances. Farther out, the spiral fraction rises. This gradient reflects the interactions that galaxies have undergone inside the cluster. Galaxy clusters start as smaller groups that merge. Infalling galaxies often come in as spirals, especially when they originate from the relatively less dense regions outside the cluster. Over time, interactions reshape them. The Coma Cluster has had billions of years in which to assemble its current structure. In that time, galaxies have fallen inward under gravity, and along the way their interactions with both the intracluster medium and with other galaxies have transformed many of them into elliptical systems. The distribution of galaxies across the cluster shows that the interior region is where those transformations have been most complete. Researchers use spectroscopic data to study the velocities of these galaxies. These velocities are not random. They reflect how the cluster gravitational potential influences each galaxy. If one plots velocity distributions, the most central region reveals a large range of speeds consistent with galaxies orbiting deep in a steep gravitational potential. The outskirts reveal slower speeds and more loosely bound systems. These spectroscopic data confirm that galaxies in the Coma Cluster are not simply drifting. They are moving at hundreds to over 1,000 kilometers per second relative to the cluster centroid. Those velocities are high enough to produce strong ram pressure effects when the intracluster gas is dense. Over time, these effects alter the galaxies that pass near the core. The difference between the outskirts and the core in galaxy population highlights the impact of environment on galaxy morphology over long timescales. Observations of the Coma Cluster have also revealed subclusters and faint streams of light called intracluster light. Intracluster light is the combined glow of stars that have been removed from their original galaxies by gravitational encounters. These stars now float freely in the cluster potential and no longer belong to a single galaxy. Their distribution and brightness patterns show where galaxies have interacted strongly in the past. Regions with strong intracluster light indicate areas where gravitational interactions were significant enough to remove stars from their parent systems. This intracluster light fills some portions of the core region like a faint diffuse glow, and its presence emphasizes that galaxy evolution inside clusters is an ongoing process. Each galaxy contributes not only gas to the intracluster medium, but sometimes stars to the intracluster light. In addition, many galaxies in the Coma Cluster show faint tidal features such as extended arcs or faint streams of stars. These features reflect recent gravitational interactions. These arcs are not dramatic spirals like one would see in an isolated galaxy. Instead, they appear as low-surface brightness structures that require long exposures to detect. Their existence signals that the galaxies in this region interact gravitationally even if they never directly collide. Interactions over hundreds of millions of years slowly redistribute stars and gas. That redistribution shapes the current composition of the cluster. Mapping all these features requires deep imaging techniques that integrate light over long exposure times. The Coma Cluster has been observed by both space telescopes and ground-based telescopes, and the combined data reveal a large-scale mosaic in which individual galaxies do not exist in isolation. The distribution pattern has been studied for decades because it reveals the large-scale outcome of galaxy evolution inside a dense environment. By comparing the fraction of different galaxy types at various distances from the cluster center, astronomers can infer the long-term trajectory of galaxies within the cluster. Most elliptical galaxies in this environment are not recently formed systems. Instead, they are older objects that have existed for very long spans of time and have had their internal gas reservoirs depleted. The distribution of galaxy types in the Coma Cluster therefore reflects a sequence in which galaxies accreted by the cluster gradually lose their cold gas and slow their rate of star formation, becoming dominated by older stars. The giant elliptical galaxies tend to sit near the center of the cluster, where the gravitational potential is deepest. They are the most massive systems and likely represent the product of multiple past mergers. They anchor the cluster core region and mark the zones where the intracluster medium is densest. The Coma Cluster galaxy distribution thus functions as a living map of galaxy evolution. And because this cluster is relatively nearby on cosmological scales, it has been a long-standing reference point for understanding the interplay between environment and morphology. Inside this complex environment sits the elliptical galaxy called NGC 4889, and it is one of the largest and most luminous galaxies in the core region of the Coma Cluster. NGC 4889 occupies a location that reflects this evolutionary path and its position in the cluster confirms that it has long been subject to the conditions of a dense intracluster medium. Its shape composition and stellar content reflect a history of long-term gravitational interactions within this environment. The central region of the Coma Cluster is a place where giant elliptical galaxies dominate the luminosity and mass budget, and this dense core is the zone where the cluster gravitational potential becomes steepest. In this region, the intracluster medium is thickest, the gas is hottest, and the overall gravitational field is strongest. The elliptical galaxies that reside here are not transient visitors. They are long-embedded systems that have remained gravitationally bound near the cluster center for extremely long timescales. These galaxies are massive, smooth, roughly spheroidal collections of stars that lack the prominent spiral arms seen in the outer cluster spirals. Their light is dominated by older and more evolved stars, and these stars produce a redder overall color because the hot young blue stars that would mark ongoing star formation are largely absent. The giant ellipticals in this region often rank among the most massive galaxies in the nearby universe. Many of them have grown large due to past mergers. Mergers are events in which galaxies combine, and when galaxies in a dense environment merge, the resulting object tends to resemble an elliptical shape rather than a spiral shape, because the ordered disk structure is destroyed. In the core region, gravitational interactions have been common over billions of years. Though direct collisions are still relatively rare because of the large distances between stars, long-range gravitational tides between galaxies have been powerful enough to mix stars, redistribute orbital energies, and erase the organized disk structure that would have existed in their past. Thus, the cluster core becomes a site where elliptical galaxies formed from the accumulated history of galaxy interactions dominate. Some of the largest known elliptical systems in the Coma Cluster sit inside this core. Their smooth brightness profile is a sign of an evolved stellar population. They contain little or no cold gas. They form very few new stars. Most of their stars are older and cooler. These galaxies reflect a state in which star formation has nearly ceased, and only long-lived stars remain to emit light. The core region is also where the dark matter density is highest. Dark matter provides most of the mass that binds the cluster. Where its density peaks, the intracluster gas becomes hottest because gravity compresses it. That heat shows up in X-ray imaging. At the same time, where the gravitational field is strongest, galaxy velocities are highest. The elliptical galaxies in the core move through the gravitational basin on orbits that reflect a deep potential. These velocities are high enough to remove gas if any remained, which ensures that the galaxies remain gas poor. The cluster core is a long-lived region of equilibrium in which hot gas, dark matter, and giant elliptical galaxies coexist. In the core galaxy, interactions over time have produced not just the large spheroidal galaxies that remain, but also the faint intracluster light created when some fraction of stars were stripped away from galaxies and left drifting freely in the gravitational basin. That intracluster light adds a faint glow that surrounds the core region, and its presence confirms the long history of tidal interactions. This faint glow is not bright enough to be visible in short exposures, but deep observations reveal it as a smooth, diffuse halo of starlight. The central region also contains relics of multiple past mergers. Some ellipticals here appear to have multiple stellar components that reflect their accretion history. These galaxies might show faint shells or layered structures in their light distribution, which are interpreted as signs of mergers that deposited stars at different radii. Each of those shells or faint outer envelopes is carved by gravitational relaxation. Even though galaxies are not solid objects, their stars follow gravitational orbits that settle into a smooth shape over long timescales. The cluster core is not silent. It is shaped by slow, continuous gravitational rearrangement. Clusters grow as subclusters fall in. The central region of the Coma Cluster likely experienced such infall in the remote past. That process would have merged multiple smaller groups into the present core. The giant elliptical galaxies that now occupy the center could be the remnants of that assembly stage. As these subclusters merged, kinetic energy of their motions heated the intracluster gas. That heating remains locked in the hot plasma that surrounds the core. Even today, temperature measurements of the intracluster medium in the core remain high, revealing the deep gravitational well beneath. Because the core ellipticals contain so much stellar mass, they are sources of many evolved stars near the end of their lifetimes. When stars evolve, they produce heavy elements inside their cores. Those heavy elements are then returned to the surrounding medium through stellar winds or supernovae. The intracluster gas in the core is enriched with those elements, because the population of old stars in the giant ellipticals produce generations of heavy element output over cosmic time. X-ray spectroscopy confirms this enrichment. The intracluster gas shows the chemical fingerprints of many generations of star formation that occurred inside galaxies long before this present epoch. The core region therefore contains not only the largest galaxies, but also the richest chemical record within the hot plasma. The existence of massive elliptical galaxies in the core also implies that enormous supermassive black holes likely sit in their centers. Observations of nearby giant elliptical galaxies in other clusters show that they tend to harbour massive black holes in their nuclei. The mass of a central black hole often scales with the mass of the galaxy bulge. Because these core ellipticals are very massive, the black holes at their centres are expected to be extremely massive as well. It is inside this environment that the galaxy NGC 4889 is located. NGC 4889 is among the largest galaxies in the Coma Cluster and sits in the region where ellipticals are concentrated. The core of the cluster is a site where extreme gravitational forces shape both gas and stars, and NGC 4889 is one of the most prominent members of this dense environment. NGC 4889 is a giant elliptical galaxy that stands out among its neighbours in the Coma Cluster core, and its luminosity ranks among the highest in the region. This galaxy is a massive, smooth, diffuse stellar system that does not display the spiral arms, dust lanes, or prominent gas reservoirs that would be expected in a galaxy with active star formation. Instead, NGC 4889 presents itself as a rounded and extended spheroid of old stars, a system that has reached a dynamically relaxed state in which stars are distributed in a smooth brightness profile that falls gradually toward its outskirts. The structure of this galaxy is roughly ellipsoidal, and its light distribution suggests a large radius and high total stellar mass. Unlike spiral galaxies that form stars in bright discrete regions along their arms, this galaxy's light is dominated by redder stars that have already evolved past the short life phases of hot blue stars. Those hot blue stars shine brightly for only a short time before they exhaust their hydrogen and evolve into cooler states. The dominance of older stars in NGC 4889 indicates that the galaxy underwent major epochs of star formation long ago, and that the cold molecular gas that once fueled those star-forming phases is no longer present in significant quantity. Such an evolved population is a hallmark of giant elliptical systems, particularly those in massive cluster cores. NGC 4889 is an example of that pattern. Its stars are not arranged in a disk. They orbit in three-dimensional configurations that form a smooth gradient of density from the core outward. The stellar orbits are randomized rather than aligned, and this lack of alignment is another sign that the galaxy does not retain the disk structure characteristic of spiral systems. Such random motions are expected in galaxies that have experienced many gravitational interactions during their assembly history. As these interactions accumulated over many billions of years, the original disks of progenitor galaxies, if any existed, would have been disrupted. NGC 4889 likely grew through mergers. In the dense core of the Coma Cluster, galaxies are close enough in space and have high enough encounter rates that mergers can play a significant role in shaping galaxy evolution. When two galaxies merge, gravitational forces scramble the orbits of stars, and the resulting object becomes a spheroidal system. If those mergers occur repeatedly, the stellar mass grows, and the galaxy grows in size. NGC 4889, given its mass and scale, is likely the outcome of multiple such events. Observations of its light profile reveal a galaxy that extends smoothly outward, with a diffuse envelope that merges almost seamlessly into the surrounding faint intracluster light. The boundary between the galaxy and the intracluster light is not sharp. That smooth transition raises the possibility that some fraction of the stars at the outer edge have been stripped away by past interactions, contributing to the diffuse halo of unbound stars around the core region. The galaxy is thus embedded not just in the intracluster medium, but also in a reservoir of intracluster light that has accumulated from many past interactions. The stellar population of NGC 4889 is dominated by older stars that produce a relatively red spectrum. This red colour arises because the light of the galaxy is dominated by cooler stars with lower surface temperatures. When astronomers observe these stars, they find that their spectral lines indicate old stellar ages and high chemical abundances, in some cases consistent with multiple cycles of star formation that enriched the gas long ago before star formation ceased. The galaxy also contains globular clusters, which are dense spherical groups of stars that orbit the galaxy. These clusters can serve as traces of the gravitational potential. Their presence reflects a long history of star formation and cluster formation in the galaxy's past. The large size and mass of NGC 4889 imply that gravity at its centre must be extremely strong, and that strength is expected to arise from both the stellar mass and the dark matter halo that embeds the galaxy. As one moves inward from the outer envelope toward the central kiloparsec, the density of stars increases dramatically. This density increase means that stars are more closely packed near the core, and these stars follow orbital paths that reflect the overall gravitational field of the galaxy. The galaxy is so massive that individual stars near the centre can reach very high orbital speeds. Those speeds can be measured by spectroscopic observations that track the Doppler shift of absorption lines in the starlight. The higher the orbital speed, the broader those spectral lines appear. Observations of the central region of NGC 4889 show that the stellar velocities rise rapidly toward the centre, and this rise is one of the clues that point toward the presence of an extremely massive central black hole. The mass of that black hole will be considered further inward. For now, the galaxy as a whole stands as an enormous elliptical system deep inside the Coma Cluster core. The galaxy is effectively the product of a very long path of galaxy evolution, during which its progenitors likely underwent multiple mergers, gravitational interactions and gas stripping events that removed their cold gas and ended star formation. The present day NGC 4889 thus offers a snapshot of a galaxy in a mature state, with its structure reflecting a final stage in which little internal evolution occurs beyond the slow passive evolution of its stars as they age. Its brightness, smooth light profile, random stellar orbits, and lack of young stars confirm that it has become an archetype of a massive central cluster elliptical. This system is the specific object that anchors the core of the Coma Cluster, and because of its size, mass and luminosity, it is one of the most important galaxies in this region to study. Inside its core lies the ultramassive black hole that forms the final target of this narrative, and the path to that centre now begins to narrow towards smaller and more densely packed scales. The light that reaches telescopes from NGC 4889 is dominated by older stars, and the spectral characteristics of those stars reveal that the bulk of the stellar population in this galaxy consists of evolved stars with lower surface temperatures than the hot blue stars commonly seen in star-forming spirals. Older stars emit more strongly at redder wavelengths, and when astronomers analyse the integrated light of this galaxy, they find that it is shifted toward the red because there are very few young stars remaining. Young blue stars live short lives, and because they burn their fuel quickly, they must have formed recently to still exist. Their absence shows that new star formation has largely come to an end inside this galaxy. Without cold gas capable of collapsing into new stars, the stellar population ages steadily as the existing stars evolve. Over time, the average colour of the galaxy grows redder as the blue stars disappear. Red giant stars and old main sequence stars dominate the emission. Optical spectra of NGC 4889 show absorption features that indicate high metallicity in many stars. Metallicity is the term used by astronomers to describe the abundance of elements heavier than hydrogen and helium. These heavier elements were produced by nuclear fusion in earlier generations of stars. Those older stars produced heavier elements and released them through stellar winds or supernova explosions. These elements were then incorporated into new stars, which means many stars in NGC 4889 have high heavy element abundance, because the galaxy experienced several star-forming epochs in its past before star formation mostly ceased. Another prominent feature of massive elliptical galaxies is the presence of large populations of globular clusters. Globular clusters are tightly bound, spherical groups of stars that orbit the galaxy at large distances. They are among the oldest stellar systems that form in galaxies. Observations of elliptical galaxies and cluster cores indicate that they often contain thousands of globular clusters. These clusters are used by astronomers as tracers of the gravitational field because they move through the galaxy's potential well on long-lived orbits. If one measures the velocities of these globular clusters, one can infer the total mass of the galaxy, including dark matter content. In a massive galaxy like NGC 4889, the number of globular clusters could be very high, and these clusters would orbit at various distances, forming a distribution that extends far from the galactic center. Globular clusters also preserve fossil information about the early epochs of star formation. Their stars are old metal-poor and stable over long timescales. Thus, the presence of such clusters in large numbers shows that the galaxy had intense star formation early in its life. As one looks inward from the outer envelopes of the galaxy toward the central region, the density of stars increases and the gravitational influence of the galaxy becomes stronger. The stellar density rises sharply in the inner regions, and the brightness of the galaxy peaks near the very core. The stars in this region move on orbits that are determined by the combined mass of the stars, the dark matter halo, and the central black hole. By measuring the speeds of those stars, astronomers can determine the gravitational field. Because light from billions of stars is blended together in a single observation, astronomers measure a velocity dispersion rather than individual velocities. Velocity dispersion is the spread in speeds among the stars. In the central region of NGC 4889, this velocity dispersion rises steeply. The steep rise cannot be explained solely by the mass of the stars. The mass required to produce such high velocities must include a central mass concentration far greater than any cluster of stars. Such a concentration is interpreted as a supermassive black hole. The mass of that black hole in NGC 4889 is estimated to be tens of billions of times the mass of the Sun. This enormous value places it among the most massive black holes known. The stellar population that surrounds this black hole does not form new stars because there is insufficient cold gas to supply star formation processes. Without cold molecular clouds, no new star-forming regions can form. The stars near the core instead represent a fossil population that has aged in place. Their dynamics provide the key to inferring the mass of the black hole. Absorption line spectroscopy shows that as one approaches the center of the galaxy, the lines broaden. The broader the lines, the faster the average speed of the stars. These speeds increase toward the nucleus. When mathematical models combine the observed brightness distribution and the observed stellar velocity dispersion profile, they can determine the mass needed to reproduce the observed orbit speeds. That mass yields the central black hole mass estimate. Thus, the stellar population is not merely a passive feature of the galaxy. It is also a diagnostic tool. The number of stars, their brightness distribution, and their velocity distribution all help reveal the invisible central mass. The stellar population of NGC 4889 therefore does not just define how the galaxy looks. It defines how the galaxy is measured. The absence of cold gas, the aging stellar population, the high metallicity and the abundance of globular clusters all point toward a galaxy that has gone many billions of years without significant star formation. It has reached a stable state in which the stars are old, the orbits are stable in a statistical sense, and the gravitational potential is dominated by a combination of stellar mass dark matter and the massive black hole in the center. The next step in this path will examine the interstellar medium of this galaxy as it exists today, because that medium has been depleted of the cold molecular gas that would otherwise fuel new stars. Only after understanding that depleted medium can the path continue inward toward the regions where the gravity of the central black hole becomes dominant. The interstellar medium inside NGC 4889 is scant, because almost all of the cold molecular gas that would be required for a new star formation has long been depleted, stripped, heated, or consumed. So the internal environment of this galaxy is defined mostly by stars, very low density, ionized gas dust at very low abundance, and the leftover relics of past stellar winds. In a spiral galaxy, the interstellar medium consists of several distinct phases that include cold, molecular gas, warm atomic gas, hot ionized gas, and interspersed dust grains. These phases interact to create star-forming regions where gas collapses under gravity to ignite nuclear fusion in dense cores. But in an elliptical galaxy like NGC 4889, especially in a cluster core environment, these phases do not exist in large quantities. The molecular gas supply is limited because the intracluster medium has stripped gas from galaxies for billions of years. When galaxies fall toward the cluster center, their more fragile gas reservoirs are removed by the ram pressure of the intracluster medium. Over time, this process starves galaxies of the material they need to form stars. Thus, the interstellar medium in NGC 4889 has been reduced to only a faint residual component. Even within the galaxy itself, any remaining warm gas is likely heated by interactions with the hot intracluster medium. This heating prevents the gas from cooling. If gas does not cool, it cannot collapse to form stars. The small amount of gas that remains is insufficient to create a stable reservoir of molecular clouds. Because the galaxy is gas, poor dust content is also low. Dust forms in cold molecular clouds and in the atmospheres of evolved stars. but in a gas-poor environment, dust grains are frequently destroyed by the hot plasma of the intracluster medium or are carried away during interactions. Observations of elliptical galaxies and cluster cores consistently show very little dust in their interiors. The dust that remains is thinly spread. Without dust to absorb ultraviolet light and re-radiate it in the infrared, the galaxy's infrared emission is weak. In spiral galaxies with active star formation, the interstellar medium emits significant infrared flux because dust warmed by young stars radiates. But in NGC 4889, the infrared signature is faint. Another way to trace the interstellar medium in a galaxy is to measure neutral hydrogen, because neutral hydrogen is the raw material from which molecular clouds form. Studies of the Coma Cluster have found that galaxies near the core have much less neutral hydrogen than similar galaxies outside the cluster. That difference is attributed to Ram pressure stripping. Therefore, NGC 4889 is expected to contain only minimal amounts of neutral hydrogen. Without significant amounts of neutral hydrogen, the formation of molecular hydrogen cannot proceed. Molecular hydrogen is the fuel for star formation. Its absence confirms that star formation inside this galaxy has stopped. The interstellar medium that remains is dominated by very low density, ionized gas heated by the radiation of old stars. This diffuse gas is barely detectable in optical wavelengths. X-ray telescopes are better suited to detect hot gas, but the intracluster medium is much brighter in X-rays than any gas inside this galaxy, so separating the faint internal gas component from the bright cluster background is difficult. Some elliptical galaxies contain cooling flows where hot gas cools slowly and settles toward the center. But in the Coma Cluster, core temperature gradients and turbulent motions in the intracluster medium may prevent significant cooling. The gas remains too hot to condense into clouds. The low-density interstellar medium in NGC 4889 is therefore both a sign and a consequence of the large-scale environment. The interstellar medium also affects the dynamical state of the galaxy. In spiral galaxies, gas dissipation can allow energy to be radiated away, which helps maintain disk structures. But in an elliptical galaxy with little gas stars orbit freely without significant dissipative processes to alter their orbits. That is part of why the galaxy retains a spheroidal shape. Without gas, spiral patterns cannot be sustained. Thus, the structure of the galaxy is tethered to the state of its interstellar medium. The gas-poor nature of this system also affects the central black hole accretion rate. Black holes grow by accreting gas. When gas is absent, accretion slows. A low accretion rate means the black hole emits little radiation. That is why the central black hole in this galaxy can be called quiescent. It is not feeding actively on dense gas. Instead, it sits in a state of very low activity. Radio surveys of some massive elliptical galaxies and cluster cores show faint radio emission from central jets. But in the case of NGC 4889, the jet signatures are weak or absent. If jets exist, they are faint. Their faint nature would reflect a low accretion rate. Some elliptical galaxies do show evidence of past bursts of radioactivity, but in the present epoch, such activity might no longer be occurring. The interstellar medium is therefore a gatekeeper between the stars and the nucleus. Without gas, the nucleus remains a sleeping object. The lack of cold interstellar fuel is the main reason that this galaxy is no longer forming stars, and the main reason that the black hole is not bright at the present epoch. The interstellar medium also contains ionized gas that can interact with cosmic rays. Cosmic rays are high-energy particles that originate in various processes, including supernovae. The old stellar population in NGC 4889 still produces evolved stars that expel material, but that material does not accumulate because it is heated, stripped, or mixed by the intracluster medium. Over time, the interstellar medium becomes a very thin residue. The line between the galaxy's own faint gas content and the hot intracluster gas becomes blurred because there is no thick reservoir of gas inside the galaxy to isolate it from the surrounding cluster environment. In this sense, the interstellar medium of NGC 4889 is more porous than that of a spiral galaxy. The cluster environment reaches into the galaxy more easily. That permeability is another sign of the mature state of this system. Because the interstellar medium no longer plays a major role, the gravitational potential inside the galaxy is dominated by stars and the central mass. The gas component is negligible. Thus, the interstellar medium in NGC 4889 can be understood as a near absence rather than a major presence. This near absence defines the next scale boundary, because the journey now proceeds into the dynamical core of the galaxy, where stellar motions trace the gravitational field more directly, and where the sphere of influence of the central black hole begins to take shape. The inner dynamical behavior of NGC 4889 becomes the next spatial layer inward, now that the depleted nature of the interstellar medium has been established. In this region, the galaxy is no longer described only by its global stellar population, but by the motions of stars and clusters within its gravitational field. When astronomers refer to galaxy dynamics, they mean the gravitational mechanics that control the orbits of stars, the distribution of orbital speeds, and the way in which mass determines those motions. The central regions of massive elliptical galaxies show very high stellar velocity dispersions because stars move under the influence of large enclosed mass. That mass includes both stars and dark matter, and in the very central portions it also includes the mass of the central black hole. NGC 4889 is known for an especially steep rise in velocity dispersion near its nucleus. This radial increase means that inner stars move significantly faster than stars farther out. The velocities of stars are not measured one by one because the stars blend together into an unresolved field. Instead, the broadening of spectral lines indicates how fast stars move on average along the line of sight. These broadened absorption lines can be compared to models, and the models allow astronomers to determine how the gravitational potential must behave as a function of radius. In an elliptical galaxy, the internal structure is supported by random stellar motion rather than by ordered rotation. Spiral galaxies rotate in a disk. Elliptical galaxies often rotate slowly or have complex rotation fields that are difficult to detect. In NGC 4889, random motions dominate. Stars near the center move in many directions and the average speeds are high. The fact that they move so fast means there must be a large amount of mass inside. These inner motions trace a gravitational well that deepens toward the nucleus. Dynamical models combine the galaxy's surface brightness profile with the measured velocity dispersion field. When both are matched, the mass distribution can be inferred. Stars follow gravitational orbits, and in equilibrium, the velocity distribution reflects the mass enclosed. If the observed speeds are higher than can be produced by the stellar mass alone, this discrepancy implies additional mass. In the outer parts of galaxies, that additional mass is generally attributed to dark matter. In the inner region, the additional mass is attributed to the presence of a central black hole. Before the mass of the black hole can be discussed explicitly, the structure of the region in which that black hole begins to dominate the gravitational field must be laid out. The portion of the galaxy where the gravity of the central black hole dominates the motion of stars rather than the combined mass of stars and dark matter is called the sphere of influence. Outside the sphere of influence, the gravitational effect of the black hole is negligible because the stellar mass enclosed by larger radii is so great. But inside the sphere of influence, the black hole's mass dwarfs the mass of the stars within that radius. In this region, stellar velocities rise sharply because they are responding to the intense gravitational pull of the central object. In NGC 4889, the sphere of influence is expected to cover a large radius because the central black hole is so massive. A large black hole expands the region in which its gravitational field overpowers that of the surrounding stars. Thus, the galaxy's inner dynamical behavior shows two regimes. In the outer inner region, stellar motions are governed by the combined field of the stars and the dark matter. In the inner region, gravitational dominance shifts to the central black hole. The transition between these regimes is subtle but measurable. These measurements must be made with great care because they require very high spatial resolution. Telescopes that measure the inner velocity field must resolve regions that are small compared to the total size of the galaxy. For galaxies this distant, the angular size of the central region is very small. Thus only the best instruments can detect these gradients. NGC 4889 has been targeted because its mass and central concentration create a velocity dispersion that is large enough to see even from hundreds of millions of light years away. Dynamical behavior in this inner region does not include ordered spiral arm rotation, spiral density waves, or bar-driven flows. Instead, it is governed by a more isotropic distribution of orbits. Stars move in orbits that are often elongated or box-shaped rather than circular. Their long-term behavior is defined by statistical equilibrium rather than by recurrent patterns. Elliptical galaxies achieve equilibrium when the gravitational potential stops changing significantly. This happens when the galaxy stops accreting large amounts of new mass. In NGC 4889, that equilibrium has long been reached. The stellar orbits reflect a dynamically settled system. The central gravitational field has been shaped by a combination of the galaxy's mass profile and the mass of the central black hole. The high densities in the central region mean that encounters between stars are still exceedingly rare in absolute terms because stars are still separated by large, astronomical distances. But the gravitational influences that define those paths are strong. If one could map each stellar orbit individually, one would see a complex three-dimensional pattern. But observations condense all those orbits into a velocity dispersion measurement that reveals only the statistical spread in speeds. Dynamical simulations can reproduce such dispersion fields. To match NGC 4889, the models require an enormous central mass. The model without a central black hole cannot produce enough velocity near the nucleus. The model that includes a massive central black hole does. Because stars respond only to mass, the mass must be present. The sphere of influence region is where this constraint becomes strongest. The boundary of calculation will soon move to that region, because that is the layer where the gravitational influence of the black hole becomes directly measurable. But before stepping into that radius, the current section must conclude with the fact that the inner dynamical behavior of NGC 4889 is defined by a strong rise in stellar velocities toward the center, and this strong rise reveals a gravitational well more intense than the stellar mass alone can explain. The central region morphology of NGC 4889 marks another narrowing step inward, because it is at this scale that the gradual outer envelope of the galaxy gives way to a more concentrated brightness profile that rises steeply toward the nucleus. Morphology here refers to the shape and luminosity distribution of the innermost galactic core, where light from densely packed stars creates an intense central glow. This glow is smooth, not patchy, which is characteristic of an old elliptical galaxy in which star formation has been absent for a long time. In spiral galaxies, the central morphology can be complicated by dust lanes, gas disks, or bars, but in a giant elliptical, like this one, those substructures are not present because the galaxy has no cold gas and no rotational disk to maintain such features. Instead, the surface brightness in the central region rises inward in a continuous gradient. The luminosity profile in this inner zone is often approximated by mathematical models that describe how brightness changes with radius. In elliptical galaxies, these profiles usually follow a smoothly curved shape rather than a sudden rise. But in the case of NGC 4889, the profile steepens strongly near the center. This steep inner slope is a visual indicator of the intense mass concentration. Light does not always map directly to mass, because mass-to-light ratios vary depending on how stars evolve. Older stars emit less light per unit mass than young stars. But even accounting for the older stellar population, the central light peak of NGC 4889 is an indirect sign that a great amount of matter is collected at the center. The key point is that the inner morphology reveals not a gentle core, but a sharply rising brightness distribution. This shape change matters because it signals a transition from the global, slowly varying stellar density of the galaxy to a region where the mass density becomes extremely high. In this morphological regime, the stars are packed more densely, and their gravitational interactions with the total enclosed mass become stronger. When astronomers analyze this inner luminosity profile, they find that it requires a central mass that exceeds what would be expected from stars alone. If the galaxy had only stars and dark matter, the central brightness slope would be shallower. The steep profile indicates that a very large central mass concentration warps the gravitational field and changes the stellar distribution. That mass concentration is interpreted as an ultramassive black hole. The morphology therefore becomes a mapping between light and gravity. The shape of the inner brightness curve is a record of the equilibrium that stars have achieved inside a gravitational well that is dominated in the central part by the black hole. Because stars in this region are old and evolved, they are not generating strong winds or supernovae that can redistribute matter significantly. Thus, the structure we see is stable. The central region morphology acts like a static fossil imprint of the forces that shaped the galaxy long ago. When astronomers attempt to differentiate between the gravitational influence of stars and the gravitational influence of the black hole, they examine the relationship between brightness and potential. If a black hole is present and is massive enough, the light profile must rise sharply near the center because stellar trajectories settle into a denser arrangement to match the inward pull. This is not compression in a direct physical sense, because stars do not pile up like fluid. Instead, over long spans of time, their orbital distribution evolves towards stable configurations that are consistent with the mass distribution. Thus, the inner brightness distribution encodes a slow dynamical response to the central mass concentration. Another morphological indicator is the central light cusp. A cusp describes a sharply rising central brightness slope. Some elliptical galaxies have shallow cores while others have cusps that rise more abruptly. NGC 4889 is an extreme case. It contains one of the steepest cusps seen in a nearby galaxy of known distance. A steeper cusp indicates more mass concentrated in the system's inner region. The relationship between cusp steepness and black hole mass has been studied in other galaxies, and in massive cluster central ellipticals the two are often correlated. In this galaxy, the extreme nature of the cusp therefore aligns with the expectation of an ultramassive black hole. The morphology also shows no signs of a nuclear star cluster. Some galaxies have small dense star clusters at their centers. These clusters are different from black holes. A nuclear star cluster is a structure of stars, only not a single compact object. But in this galaxy, no such structure is dominant. Instead, the bright core reflects a smooth profile that signals a gravitational regime defined by a point-like mass, far heavier than any star cluster could be. The absence of dust lanes or star-forming rings means that the light distribution is not obscured. The central region is optically transparent because there is little gas or dust to block the starlight. Therefore, the observed morphology is not distorted by extinction. What one sees is an unobscured view of the stellar structure. This clarity increases confidence that the central rise in brightness is genuine and not an artifact of dust absorption. The stability of this morphology is also notable. Because the galaxy is not accreting gas and is not forming stars, the central region is not undergoing rapid change. No new stellar populations are forming to alter the luminosity distribution. No gas is inflowing to feed the black hole. Therefore, the inner morphology represents a nearly static equilibrium state. The steep brightness slope is a stable feature supported by the current distribution of stellar orbits and the gravitational potential. This morphological layer must serve as the final outer boundary before crossing into the zone where the gravity of the black hole itself becomes the dominant controlling force over stellar motion. The luminosity profile sets the scene. The stars are arranged in equilibrium near the massive central object. The central brightness peak is a signpost marking the gravitational rise. The slope of that peak serves as a spatial transition. It says the next step inward will leave the domain where mass is dominated by stars and enter the regime where mass is dominated by a single central black hole. The sphere of influence is the region around the central mass in which the gravitational pull of the black hole exceeds the gravitational pull of the combined stars within that same radius, and this region marks a physically distinct transition between ordinary galactic gravity and the dominance of the compact central object. The radius of this sphere is defined conceptually by the point at which the enclosed stellar mass equals the mass of the black hole itself. Outside that radius, the gravitational field experienced by stars is shaped mostly by the cumulative mass of stars and dark matter. Inside that radius, the mass of the black hole dominates the potential. In a galaxy like NGC 4889, where the black hole mass is estimated to be tens of billions of solar masses, the sphere of influence becomes comparatively large in physical units. This creates a region where the velocities of the stars respond directly to the gravity of the black hole. Those stars move at speeds that cannot be reproduced by any plausible stellar mass distribution alone. The velocity field near the nucleus reveals this sphere by the way the velocity dispersion rises toward the center. The stars in this region are not orbiting in simple circular paths. Elliptical galaxies do not form disks or bars in the way spirals do, so the orbital structure is more complex. Nonetheless, the speeds depend strongly on the total gravitational potential. A massive black hole forces stars to travel on trajectories that average to higher velocities. This effect produces spectral line broadening because the light from all these stars arrives blended together. That broadening becomes more obvious close to the central point where the gravitational well deepens sharply. The observational challenge is that this radius, even though physically large in terms of the galaxy's internal scale, is still very small on the sky because NGC 4889 is hundreds of millions of light-years away. Resolving this sphere in angular units requires instruments with high spatial resolution. Without that resolution, the inner light becomes blended into larger bins, and the velocity distribution appears averaged over too large a region. Only when data are obtained at very fine spatial sampling can the rise in velocity dispersion be mapped sufficiently. When that mapping is achieved, the radius at which the velocity field transitions provides the measurement of the sphere of influence. Because the black hole is so massive, the sphere of influence for NGC 4889 is large enough to be detected even from this distance. The sphere of influence concept allows astronomers to separate the gravitational contributions of stars from the gravitational contribution of the black hole. The stars inside this region are not special in their composition or age. They are simply located in a place where the central mass dominates their orbits. Over time, stars in this region can be deflected into very elongated paths. If a star's orbit takes it too close to the black hole, tidal forces can disrupt it, producing stellar debris. But such events are extremely rare because stars are spaced far apart. Still, this region is where such processes could theoretically occur. The sphere of influence is a place defined not by new matter compositions, but by the relationship between mass distribution and orbital dynamics. The behavior of the stars is constrained by the requirement that they remain gravitationally bound. If total enclosed mass increases sharply inward, the velocity field must reflect that change. The observational data for NGC 4889 place a very large mass in the central region. That mass is inferred because no distribution of stars can accomplish this velocity increase. Thus, within the sphere of influence, the motions of stars provide direct evidence that a compact object resides at the center. If the central mass were something other than a black hole, it would have to take up space. If it took up space, its density would have to be lower. But a lower density object would produce a shallower gravitational potential. The observed velocity slopes are steep enough that they demand an object extremely compact and extremely massive. A cluster of black holes could not remain stable for billions of years. A cluster of neutron stars could not maintain this configuration. A cluster of ordinary stars would collapse or disperse. The only configuration stable enough to remain unchanged on cosmic timescales, given the mass inferred, is a single black hole. The sphere of influence boundary is where the change in dynamical control becomes explicit. At radii larger than this, the stars respond to the total mass of the galaxy. At radii smaller than this, the response of the stars reveals the mass of the black hole itself. When discussing the central mass, one must not yet leap ahead to the terms horizon or event horizon, because those features lie deeper inward still. The sphere of influence is not a boundary associated with the physical edge of the black hole. It is a dynamical boundary defined by gravitational dominance. Stars in this region orbit at velocities set by the central mass. They do not fall in as gas would because there is no dense gas to accrete. Instead, they continue to orbit, forming a steady velocity field. The hot intracluster medium beyond the galaxy does not penetrate deeply inside this region, because the sphere of influence is governed by the mass of the black hole, not by the external medium. Therefore, even though the intracluster medium surrounds the galaxy, it does not directly govern the motion of stars inside the sphere of influence. The boundaries of this region are set not by pressure or temperature, but by gravitational potential. The sphere of influence is thus a concept that provides a clean definition of scale. Beyond this radius, the black hole is irrelevant to galactic kinematics. Within this radius, it is paramount. That radius must now serve as the final quantitative limit of the stellar-dominated region, because the next step inward in this narrative must proceed into the mass scale of the black hole itself, where the properties of the compact central object must be treated directly without reference to the stellar distribution that surrounds it. The basic parameters of the central black hole in NGC 4889 represent the next inward step because the sphere of influence has now been defined conceptually as the radius within which stellar motions respond primarily to this compact mass, and therefore the mass of the black hole itself must now be described in terms of what is known what is measured and what remains uncertain. The central black hole in this galaxy is classified as an ultramassive black hole, a term used for black holes with masses on the order of several billions of solar masses or higher. In this specific case, the mass estimate sits in the tens of billions of solar masses range, which places it among the most massive black holes confirmed in the nearby universe. Such a value places it above the typical mass range seen in supermassive black holes at the centers of ordinary galaxies, because those more common systems may contain black holes on the order of millions or 1 billion solar masses, whereas this galaxy contains a central mass that is more than an order of magnitude larger. The measurement of the mass arises from matching dynamical models to the observed stellar velocity dispersion and light distribution. Such models must include the stellar mass profile, the dark matter halo contribution, and the additional point mass at the center. By adjusting these parameters to reproduce the observed line broadening from stars very close to the center, the black hole mass can be inferred. The fact that different modeling approaches produce similar mass ranges strengthens confidence in the estimate. The mass is not infinite, it is finite but extremely large. A mass of tens of billions of suns means that this object contains more mass than all the stars in some entire small galaxies. Because gravity depends on total mass, such a black hole exerts a gravitational pull extreme enough to dominate the motions of stars inside the sphere of influence. Yet despite this enormous mass, the black hole remains invisible directly. Black holes do not emit light. They are detected by their gravitational effects. In this narrative, the vast mass is the defining physical property. Other parameters include the spin of the black hole, a quantity that describes how fast it rotates. The spin of this object is not measured directly. The methods used to measure spin more reliably require bright accretion disks because spin affects the inner regions of an accreting disk and changes how close the orbiting material can approach before falling inside the event horizon. But in this galaxy, the accretion rate is low, so the black hole is quiet. Without strong radiation from a disk spin cannot be measured accurately. Therefore, the spin of this black hole remains uncertain. Its charge is also unknown. Black holes in astrophysical environments are expected to be nearly electrically neutral, because any net charge would attract opposite charge from the surrounding environment and neutralize quickly. Thus, no significant charge is assumed. The most fundamental parameter that can be measured reliably is mass. It is mass that controls the gravitational field. It is mass that sets the radius of the event horizon. The event horizon marks the boundary within which the escape velocity equals the speed of light. That concept will be treated at a later inward step. At this current scale, the mass of the black hole is the principal fact. The mass can be written as tens of billions of solar masses, but because the exact number carries uncertainty, due to modelling assumptions, it is best understood as a range. Still, even the lower bound places it in a category far above more common supermassive black holes. Such a mass suggests a long history of growth. Ultramassive black holes at galaxy centres may grow by merging with other black holes, or by accreting gas during phases when the galaxy had abundant fuel. In the present epoch, NGC 4889 shows no major accretion activity. But that does not rule out periods of high accretion in the distant past. Measuring the mass of this black hole requires understanding which scales are resolvable. The physical size of the sphere of influence grows with mass. The larger the mass, the larger the radius at which the black hole dominates gravity. This is why this particular black hole can be detected at a distance of hundreds of millions of light years. If the black hole were less massive, the sphere of influence would be smaller, and resolving it would be more difficult or impossible with current instrumentation. Because the sphere of influence is resolved, the mass estimate is credible. The uncertainty in the mass reflects uncertainties in how stars are distributed and uncertainties in how dark matter contributes to gravitational fields at small radii. If one assumes different dark matter profiles, results change slightly, but the mass remains enormous under any realistic assumption. The existence of such an ultra-massive black hole also serves as a reference point in the study of galaxy-black hole coevolution. Observations of galaxies have shown correlations between the mass of the central black hole and the mass of the bulge or elliptical component of the host galaxy. These relationships suggest that black hole growth and galaxy growth may be connected over long timescales. NGC 4889 fits into these correlations at the extreme end of the distribution. It is one of the largest galaxies in the cluster, so a black hole of enormous mass would not violate these relationships. On the contrary, it fits the idea that the largest galaxies host the most massive black holes. The basic parameter of central mass therefore links this galaxy to a broader pattern found across the universe. Other basic properties include the physical scale implied by the mass. The radius of the event horizon will be very large in absolute distance units compared to black holes of lower mass. It will still be small compared to the galaxy as a whole. But compared to stellar-sized black holes, it will be immense. Because this black hole is quiet, it produces no bright accretion disk. Without such a disk, the region outside the event horizon is not luminous. The lack of radiation does not diminish the gravitational presence. Instead, it underscores that this object is a sleeping mass that only reveals itself indirectly. Thus, the main basic parameter of this black hole is mass. Other parameters remain unknown or unconstrained. The mass is so large that it defines nearly every aspect of the gravitational environment in the central region. The next step inward must turn to the current state of accretion, because the mass defines the potential, while the accretion state defines how active the black hole is at the present epoch. The accretion state of the central black hole in NGC 4889 is defined by the fact that this object is quiescent at the present epoch, meaning that it is not actively feeding on a substantial supply of cold gas, and therefore it is not generating the intense electromagnetic radiation that is characteristic of bright active galactic nuclei. Accretion is the process in which matter crosses a region close to the event horizon and radiates gravitational energy as heat and light before crossing the boundary. In luminous quasars, large amounts of gas fall inward and form an accretion disk that shines brightly in ultraviolet and X-ray bands. But in this galaxy, the interstellar medium does not contain enough cold molecular gas to sustain such a disk. Without cold gas, there is no reservoir from which dense flows can form. With no dense flows, there is no bright accretion disk. The absence of strong accretion means that the black hole is quiet. This quietness is why this object can be described as sleeping. It is not reacting strongly to the outer environment, it simply curves space-time and remains dark. Observations of NGC 4889 reveal no bright emission from its nucleus. There is no strong ultraviolet excess. There are no broad emission lines in optical spectra that would indicate gas being excited or ionized near the black hole. The central radio emission is weak or absent. This weak signature is consistent with a very low accretion rate. In some giant elliptical galaxies, faint radio jets persist, even when the accretion rate is low. But jet power correlates with accretion and magnetic field configuration. In NGC 4889, any such jets are very faint. The galaxy does not display the typical radio lobes that would be expected if the nucleus had recently powered a high-energy outflow. In some cluster central galaxies, periodic feedback cycles occur in which the black hole alternates between quiet and active states. In those cases, the intracluster gas cools, slowly sinks inward, feeds the black hole, triggers a burst of accretion, and launches jets that reheat the gas and suppress further cooling. That feedback cycle can repeat many times. But in this galaxy, that cycle does not appear to be operating strongly at present. The intracluster medium remains too hot and too turbulent to cool effectively. Because cooling is not efficient, no new gas supply reaches the center. Without that supply, accretion remains low. The nucleus remains dormant. Dormant does not mean inactive in an absolute sense. Even at extremely low accretion rates, a trickle of matter may approach the horizon. But the luminosity produced is negligible. It is not detectable against the light of the host galaxy. Thus, although matter may fall inward slowly, that inward flow is not enough to power a bright nucleus. The accretion flow regime under such conditions is thought to produce radiatively inefficient accretion. Radiatively inefficient flows convert only a small fraction of gravitational energy into radiation. Instead, most of the energy remains in the gas as kinetic heat, or is carried into the black hole. This reduces the luminosity further. Observations cannot distinguish fine details of the flow regime here, because the luminosity is too low to measure specific spectral signatures. But the absence of bright accretion features means that the general classification of this nucleus is that of a radiatively inefficient state. Another feature of a quiescent black hole is that the jets, if present, are faint. Because jets require magnetic fields anchored in accreting plasma near the horizon, low accretion reduces jet power. In NGC 4889, any such jets are not strong enough to carve cavities in the intracluster medium. In some cluster cores, cavities blown by jets are observed as depressions in X-ray maps. They indicate past radioactivity, but in this galaxy such cavities are not evident. That absence likely means that the black hole has not driven strong jets in the recent past. The accretion state also influences the physical structure of the region just outside the event horizon. In bright systems, that region may contain a hot corona of plasma that emits X-rays. In this galaxy, the corona would not be luminous enough to detect. The black hole therefore remains simply a gravitational mass with no bright emission. Its influence is felt only by the motion of stars near the center. The quiescent state does not imply that the black hole will remain quiet forever. Conditions could change over cosmic time. Galaxy mergers or interactions could bring fresh gas to the center, but that possibility lies outside the bounds of the present epoch and outside the allowed narrative scope because this documentary structure does not permit foreshadowing. The only permitted description is the present state. In the present state, the black hole is quiet. The accretion luminosity is negligible. The nucleus is dark. Light from the surrounding stars dominates all optical emission. The galaxy provides no visual cue of the extraordinary mass that resides inside. Thus, the basic parameter of mass described in the previous section now combines with the description of accretion state to form a picture of a black hole that exists as a gravitational well without radiative output. It behaves as an invisible anchor. The absence of accretion means the system remains stable and unobtrusive. The large-scale intracluster environment remains hot and does not deliver gas inward. The interstellar medium inside the galaxy is depleted. Therefore, the black hole sits in equilibrium with no bright disk. The next stage inward must move to the physical definition of the event horizon, because while accretion describes what the black hole is doing now, the horizon describes what the black hole is. The horizon marks the limit beyond which light cannot escape. It is not a physical surface in the traditional sense, but a theoretical boundary defined by geometry. That boundary will be the next inward layer, The event horizon is the boundary in space-time beyond which no signal or particle can escape the gravitational field of a black hole, and this boundary is not a material surface, but a geometrical surface defined by the point at which the escape velocity equals the speed of light. And because the speed of light is a limiting velocity in general relativity, anything that crosses this boundary cannot return information to the outside universe. The radius of the event horizon depends directly on the mass of the black hole. For a non-rotating black hole, this radius is called the Schwarzschild radius. If a black hole rotates the horizon, shape becomes more complicated, but the fundamental concept remains that the event horizon marks the place where outward-directed light signals cannot escape. In an ultra-massive black hole with mass of tens of billions of suns, the event horizon radius becomes extremely large in physical distance units. It is still tiny compared to the scale of the galaxy as a whole, but compared to the horizon of stellar mass black holes, it is enormous. The event horizon is the point of no return. Matter that crosses the horizon cannot emit radiation that reaches observers outside. Any information about what happens inside cannot reach the external universe. General relativity states that space-time curvature becomes so severe inside this region that all future directed paths lead inward. Outside the horizon, space-time is curved, but not so extremely that escape is impossible. The radius of the event horizon for this black hole can be calculated from the mass. Because the mass is extremely large, the radius may span a size that could in principle contain the orbits of entire planetary systems, if such systems existed there. But there are no planets in that region. Inside this galaxy, stars orbit outside the sphere of influence radius, but do not orbit near the horizon. No star is observed that close. The horizon remains a theoretical boundary that cannot be imaged directly. Observing the horizon requires resolving extremely fine spatial scales. For nearby black holes such as the one in the galaxy M87, or the one at the centre of the Milky Way radio interferometry, has measured regions near the horizon. But NGC 4889 is much farther away, hundreds of millions of light-years distant, and the horizon is far too small in angular size for current instruments to resolve. Therefore, although this horizon exists physically, it is inferred rather than seen. The presence of the horizon is guaranteed by the existence of the mass concentration described earlier. If one accepts general relativity as the correct theory of gravity, a mass this large must have a horizon. The horizon is not a hard surface. Nothing strikes it in a conventional sense. Matter simply follows geodesics, which are the paths of least action in curved spacetime, and those geodesics lead inward once the boundary is crossed. Photons inside the horizon cannot propagate outward. They are trapped. The horizon therefore divides spacetime into an exterior region available to external observers and an interior region from which no information can escape. The horizon also defines how close stable orbits can form for matter and light outside the black hole. There exists an innermost stable circular orbit which is located outside the horizon. If gas or matter were present in a disk, that disk would extend inward only to that stable orbit before the plunge region begins. But in this galaxy, there is no luminous disk. Thus, stable orbits are only theoretical here. The region inside the horizon is not part of observable physics. When discussing the horizon, one must avoid conflating it with the singularity. The singularity lies further inward, where classical general relativity predicts infinite curvature. But this narrative cannot describe that region because it is inside the horizon, and therefore not part of observable spacetime. The current scale is the horizon, which is still a boundary that can be defined from the outside. The horizon is the last definable scale that has a physical meaning accessible from exterior measurements. Everything deeper is beyond observational access. The horizon is not static in principle. If the black hole accretes more mass, the horizon would expand. If mass is lost in hypothetical processes, the horizon would shrink. But in the current epoch, this black hole is quiescent. Thus, the horizon size is not changing on any measurable timescale. In this galaxy, the lack of accretion means the horizon is not surrounded by a luminous environment. It sits in darkness. Stars orbit far outside. No inner accretion flows glow brightly. The horizon is therefore not lit by an accretion disk. The region near the horizon is profoundly empty in terms of observable matter. The horizon exists as the boundary between the known and the unknowable, between space-time that allows communication and space-time that forbids it. The recent direct imaging of shadows of nearby black holes showed that horizons can be inferred from the way light bends around them. But because NGC 4889 is so distant, no such shadow image exists here. The horizon remains a theoretical surface that can be calculated but not seen. It is the unavoidable implication of combining a mass of tens of billions of solar masses with the geometry of general relativity. The horizon now marks the second to last inward layer of this system. The next inward layer is the region extremely close to this boundary, where strong fields and rapid spacetime curvature define the final, observable physics, the innermost physics that can still be discussed in an observationally meaningful way, are the relativistic effects that occur just outside the event horizon in the narrow region where space and time become steeply curved, but not yet sealed off from the external universe. And in this regime, the predictions of general relativity are not approximations, but exact statements about how clocks run, how trajectories bend, and how energy and momentum behave. Near the horizon of an ultra-massive black hole, the curvature of spacetime is severe, but the local tidal forces can be less violent than one might expect, because tidal forces scale inversely with mass at the horizon, meaning that, although the gravity is extraordinary, the gradient of that gravity from head to foot of a hypothetical observer would be lower than around a smaller black hole, because the horizon is so large. Nonetheless, such an observer cannot exist here because there is no stable platform for matter to rest this close to the black hole in NGC 4889. No matter is present in significant density, and the region is not filled with glowing plasma or bright emission. Instead, the region is defined by curvature itself. The theory predicts that near the horizon, light paths bend sharply. Time runs slower relative to distant observers, and any photon trying to climb out from near the horizon loses energy, meaning its wavelength is stretched. This gravitational redshift increases as the horizon is approached. If matter were to orbit near this region, the innermost stable circular orbit would mark the limit of stable orbital motion. Inside that orbit, matter would plunge inward. But because this black hole is in a quiescent state, there is no bright disk, and therefore there is no observational signature of that orbit. The region remains theoretical in the sense that its physical effects on matter cannot be measured here, because matter is not present in the densities required to emit detectable radiation. In black holes that are actively accreting the inner region, becomes a laboratory for studying high-energy emission jet-launching mechanisms and magneto-hydrodynamic processes. In such systems, the physics near the horizon manifests in the emission spectra, the variability of light curves, and the shape of the iron K-alpha line in X-ray spectra. But none of those signatures can be applied here because the nucleus is dark. Thus, the only physical statement that can be made about this region in NGC 4889 is that it exists as a gravitational domain in which general relativistic curvature dominates. The space-time metric near the horizon is described by the solutions to Einstein field equations for a rotating or non-rotating black hole. Those equations define how space is curved, how geodesics behave, and how light cones tilt inward as the horizon is approached. For a distant observer, nothing appears to cross the horizon. Instead, signals slow and fade. But that appearance is due to the extreme redshift that light experiences. In reality, any object crossing the horizon experiences no special local boundary. But because no information can be sent outward from inside, the crossing cannot be observed. This asymmetry between coordinate time and proper time is one of the central features of general relativity. The inner physics zone here is therefore not a place where new structural components exist. It is a place where classical intuitions break down. Newtonian gravity cannot describe the behavior of objects near this surface. Only general relativity can. In an active system, magnetic fields anchored in plasma near the horizon could twist and launch jets. But in this sleeping system, no such plasma is present. Thus, the magnetic field structure near the horizon is unknown. The quiescent state of the galaxy means that the inner region remains free from luminous matter. The curvature alone defines the environment. If one traces a bundle of light rays near the horizon, the bending is extreme enough that light can orbit temporarily in unstable circular paths. Such photon orbits lie outside the horizon, but inside the region where stable orbits for matter would exist. In luminous systems, these photon orbits produce distinctive bright rings in interferometric images. In this system, the photon orbit is still present as a geometrical surface, but cannot be seen because no bright matter illuminates it. Thus, in this galaxy, the photon orbit remains invisible but real. The innermost physics region in NGC 4889 is therefore defined by mathematical structure rather than by direct measurement. The existence of this region follows inescapably from the existence of the mass, and from the assumption that general relativity is correct. The structure of space-time in this band defines how trajectories behave. Any test particle or photon in this zone would follow geodesics extremely different from those seen at large radii. The time dilation near the horizon is severe. A clock near the horizon would tick far slower than a clock in the outer galaxy. This difference reflects the strong curvature of space-time. Because the black hole is quiescent, there is no observable emission near the horizon to measure this effect. But the mathematical structure remains. The central object therefore defines a region where physics becomes governed entirely by gravity geometry and general relativity's curvature equations, rather than by thermal processes or fluid dynamics. The innermost physics zone is not a place of luminous turbulence. It is a place where curvature alone controls all motion. Nothing in the observable universe can escape from inside the horizon. Thus the boundary of accessible physics stops here. No signals from deeper layers exist. Therefore the narrative cannot proceed past this radius. This innermost physics zone is the final layer that remains accessible from outside without crossing the horizon. And so the scale must stop at this surface of last observation before the final winding down of the documentary. The region extremely near the event horizon completes the inward journey, because at this final scale the gravitational field has already reached a regime in which curvature governs all motion, and there is nothing smaller in physical space that can be described from external observation, since there is no matter to illuminate these depths, and no photons leave this region to encode information about the geometry directly. So the last scientifically accessible layer concerns only the outer skin of general relativity. the invisible mathematical surface that encloses the black hole in NGC 4889, and this region must now be described in purely external terms, because there is no observatory in existence that can resolve the horizon of a black hole, hundreds of millions of light-years distant, and therefore this inward view must terminate at the theoretical edge. The horizon of this black hole can only be computed through the mass estimate, and because the mass lies in the range of tens of billions of suns, that horizon would be correspondingly large in absolute spatial extent. However, even a large horizon does not produce a visible shape because black holes radiate nothing from the horizon. In systems that accrete gas, the horizon is outlined by the radiant inner edge of the disk, by the hot corona, or by the base of magnetically anchored jets. But in this galaxy there is no bright disk, no luminous corona, no outflow, no shock-heated atmosphere, and therefore the horizon is not illuminated by any natural tracer. Its existence is inferred by the stellar velocity field outside it. That velocity field has already been described. The stars orbiting near the centre move fast enough that the dynamical models require the presence of an ultra-massive black hole. The sphere of influence establishes the central mass. The central mass demands a horizon if general relativity is correct. Thus the horizon is guaranteed. Beyond that, nothing else can be directly observed. General relativity states that space-time curvature near the horizon depends only on mass, spin and charge. Spin and charge are not measured here. Mass is measured, so mass plus general relativity yields the horizon radius. The radius is smaller than the resolution of any telescope, so the horizon never appears as an image. There is no ring of infalling plasma to silhouette it. The only visible light in the central region comes from stars far outside. The horizon therefore sinks below the threshold of detectability. The interior of the horizon cannot be discussed because it has no observable influence on astrophysical objects outside. Classical general relativity treats the horizon as a one-way boundary. Any influence from inside does not escape. Thus, the observational universe ends here. Because the interstellar medium is depleted, there are no molecular clouds drifting inward. There are no tidal streams being pulled apart. There are no stars caught in plunging orbits. Everything is quiet. Nothing is interacting with the horizon today. There is no hot disk to cause spectral lines to broaden into relativistic shapes. There are no jets to carve cavities in the intracluster medium. All that remains is the mass itself. That mass curves space-time and produces a potential deep enough to bind the orbits of nearby stars. The horizon sits in darkness. The galaxy sits in the dense core of the Coma Cluster. Above the horizon lies empty space, scattered evolved stars, faint ionized gas, and the geometry of a region in equilibrium. The black hole does not alter that quietness because it has no fuel to do so. There is no accretion engine running today. There are no luminous changes to record. The horizon marks the lower limit of information. Nothing below that limit participates in the universe of signals. The horizon is the dividing line between the region that interacts with the rest of the galaxy and the region that cannot interact. The geometry outside this horizon is static on human timescales. The horizon does not fluctuate in size because mass flow is negligible. Thus the shape of space-time here is steady. There is no outflow to disturb the surrounding region. There is no disk to exert radiation pressure. The black hole simply exists invisible and silent. Because we cannot observe deeper than this boundary, the physical narrative must end here. Astrophysics is observational physics, and observational physics stops at horizons. In this galaxy, the horizon does not glow. There is no experimental handle on its interior. All that is known is that the central mass exists curves space-time and sits at the bottom of the gravitational potential well. Above it, the brightness of evolved stars traces the equilibrium of the galaxy. Outside that region, the gas-poor interstellar medium signals the absence of star formation. Beyond that, the giant elliptical morphology reflects the history of mergers and tidal interactions. Further outward still, the galaxy population in the Coma Cluster core demonstrates the cluster's long history of stripping and dynamical reshaping. And at the larger scale, the intracluster medium reveals the gravitational depth of the cluster and the dark matter content that binds it together. Everything in this chain of nested scales has been traced from outer to inner. Each region was complete before the next step inward began. Each layer connects to the next through geometry, mass, and dynamics. All inward paths culminate here at the horizon, because there is no deeper layer that can be discussed without leaving the observable universe. The ultramassive black hole in NGC 4889 therefore stands not as an engine of radiation, but as a static gravitational endpoint. It represents the final interior of a galaxy that has gone dormant. It is the lowest rung of the outer accessible scales. It cannot be probed, it cannot be imaged, it cannot be illuminated. And so the narrative ends at the boundary where physics becomes inaccessible, where space-time curvature hides its interior, and where no further inward step exists that remains compatible with the requirements of observation.